Good morning, everyone. Thank you for tuning in to our program, the Language Circle. And as a matter of fact, it is apparently Italian week at the Language Circle. So we start with an Italian PhD student in the room, Lorenzo is here. And then our first speaker of this week is Giovanni Di Liberto, who came all the way from the beautiful Italian town of Dublin. And then tomorrow, we will have also another Italian speaker, Luigi Grisoni from Berlin. So it helps us to have this in our gray Leipzigian fall climate. Yeah, I know that's an ugly introduction, but anyway. Welcome, Giovanni. I'm very happy that you made it to the Language Circle and that you stuck to this date, even though you have a slight cold, but I trust you can still manage. Giovanni is an assistant professor in intelligent systems at the Trinity College. He holds a PhD in auditory neuroscience from Trinity as well, and he received his bachelor's and master's degrees from Padua in Italy, of course. You're not surprised by that. He performed his postdoctoral research at the École Normale Supérieure under the supervision of Alain de Chavagne and Shihab Shamma before moving back to Dublin. So Giovanni's scientific interests, and most of you may be familiar with these, but I'll list them again for the people who are unfamiliar with his work, center on understanding the brain mechanisms underlying speech comprehension. And he's really bringing an engineer's perspective to this. And I think that's really refreshing for a field that is like a traditional genesis in the humanities, psycholinguistics, maybe even linguistics proper, and having engineers on board is, I think, crucial to becoming more systematic, more experimental, and so on and so forth. So I'm watching his work closely, and I like it a lot. He's famous, I think, for developing data analysis methods that many of you may have used in the past, also applying them himself, of course. And recently, he has also turned to performing translational research. For example, the development of BCIs, or objective measures for the monitoring of language development and healthy aging. So that sounds promising, and we're looking forward to future work. Before we start the talk, I have to make one announcement. One today, right? Thank you, Caroline. The announcement is that you cannot unmute yourselves, dear audience, and we're very sorry for that. So in the discussion, if you want to raise a point, if you want to ask a question, you please have to raise an icon or something, or type something in the chat, so we know that you want to ask a question. And Carl was happy to pass the mic to you. That's just a safety measure because we've had some issues in the past with pirates really in the beautiful Language Circle, and we don't want pirates in the Language Circle, so we have muted everyone. All right. Without further ado, I want to pass the microphone now to Giovanni, and we are very, very happy that you made it to the Language Circle today.
Thanks a million. This is super, and like I have to say, I'm really happy with the invitation. I'm sorry I can't be there in person, and some of you, I think, will find the talk is involves work that is relevant to some of the other talks that you had previously. I think Benjamin is in the call, for example. He presented very relevant work as well. So I'll just jump straight into it. So since I sometimes forget, I decided to start with the acknowledgements from now on. So I just wanted to acknowledge, before I get into the work, my mentors. Ed is my PhD mentor, then Alan and Shihab, they were my postdoctoral supervisors, and they are still my mentors. And Usha and Nima, they were instrumental to some of the work I've done and to some of the entire trajectories I've taken. And then, of course, lots of colleagues that are involved in the work I'm going to talk about. So just to keep things simple, this is everything about language, right? And So I'm going to talk particularly about speech, but I also wanted to mention a couple of results on the music side of my research, which are also relevant for speech and language. So I don't need to tell you why studying speech is important, but there are two angles that I want to clarify. So one angle that I take is try to understand how speech processing works. And the other angle that I take is to use speech processing as speech as a task to try to study other processes. So, for example, we know the speech is a complicated process that involves various cognitive functions, prediction, attention. So you might use speech as a way to study those cognitive functions. And also then for studying, for example, language-related deficit, and potentially going towards more, brain-computer interfaces or intervention. So in terms of data, what I use is, I'm going to talk primarily about EEG. We also bought now in Trinity College in Dublin an OPM MEG, which is getting quite a bit of interest because it's more affordable than to maintain than the traditional SQUID MEG. So we got one of those where, and I'm going to use it heavily, I think. And then also use pupillometry and whatever is necessary for the studies, for the questions, for answering the questions that I'm interested in. So the idea, and I'm going to go through the first part very quickly because you probably have seen it already. So tell me if it is obvious and you want me to skip it. But basically the concept is we have experiments where people listen to speech and we record the neural signal, right? Neural signals from, for example, EEG. And the idea is that the neural signal is primarily garbage, but then there is also something good behind this highly noisy signal. Now, what we were using at the start was the acoustic response, the correlates of acoustics, but we know that there is much more going on behind that noise. So there is phonology, encoding of predictions, semantic, lexical predictions, and so on. So there is a lot of potentially interesting markers in there that we may want to measure to answer our questions. And this comes from a time where we couldn't really study continuous stimuli easily, right? And most of research was based on event-related potentials. So you want to study syllable processing or phonological encoding. The experiment has to be tailored to study one particular contrast, for example, ba versus ga. So there are plenty of studies that are limited to 3 different syllables, for example, and that's great. It's very useful, but it's not naturalistic speech. And for example, in the context of a syllable, we know that the acoustic of a syllable is going to change due to co-articulation and so on. So I wanted to study naturalistic speech, and there is a number of reasons. As I said, ecological validity, but also it's more applicable in challenging cohorts. So if you want to take children that are, 8 years old, it's easier to get them to watch a cartoon than to listen to isolated syllables for a certain duration of time. Then there is also another element of the interaction between processes. If you play syllables, you can't study the interaction between syllable and lexical encoding or so on and so forth easily. Or at least you can just study 1 or 2 things for each experiment when you talk about ERPs. So the idea was, okay, what did we have? This is 2013 when I started my PhD, and what did we have? What we knew at the time was that when you have EEG and you have and the stimulus envelope, for example, speech envelope, so the change in magnitude over time of the speech sound, we knew that there is a relationship between the two. The relationship is reliable and can be used for a number of reasons. But how do we measure it? So this is going to be relevant to the entire talk. So one metric is how much variance in the EEG can be explained by the envelope. And the other metric is what is the relationship and the time latencies that best describe this relationship. So if you hear a beep, for example, you know that the beep is going to take some time to be processed in the brain. Same thing when you hear any variation in the acoustic input, that's going to take some time. And so these models that I'm talking about, they account for these time latencies. And so one metric is how well is the EEG encoded, and the other is describing the time latencies that matter for that relationship. So that's primarily work from my PhD supervisor at Lawler, and MTRF toolbox that is used by quite a few people now. The work was led by Mick Cross. The other angle is that we can also do decoding, and we'll talk about that in a second. But let's get to the present now for a second. So this was over 10 years ago, and everything we had was the envelope. Now the idea is that let's stay here a second. You extract some features from the speech, and then you relate them with the EEG. So the model is linear, right? That's the kind of models we use. They're linear lagged regressions. They are regularized, and I can say more about that if you like. But the relationship is not really linear, right? We know it's non-linear, but these linear models, they actually allow us to study these non-linear mappings by working with non-linear feature extraction. So you take your speech and you get your spectrum, and then you get your phoneme categories, and you get your lexical surprise, etc. So whatever feature you can get features that are non-linear mappings from the speech. So the model really is a non-linear model in function of the speech. Then the way it's calculated is linear, which allows us to more easily interpret what's going on. So if you have your inputs, and here you have what I mentioned before, so the spectrum, which is the acoustics, one element of the acoustics. Then you have the categories in terms of phonetic features, phoneme surprise, word surprise that you can get from GPT, for example, from large language models. So you saw this also in a previous talk. I think it was in 6 months ago or so by Benjamin. I don't know if I pronounce it right, Morillon. So you take a bunch of features and you try to predict your EEG. So again, how much variance can you explain, but also what is the time lagged relationship? So now people use all sorts of features depending on the questions they want to tackle. But at the start, what we had was acoustics. And then the idea was, okay, let's try to study the next stage, which is phonological encoding. From my perspective, anyway, it was the next logical thing to study. And so what I did there was to take play an audiobook to was it 10 listeners in the first experiment, then it was 20. Anyway, we played audiobooks. Then I did a time alignment, a phoneme tagging. And so we knew at what time point each phoneme was present. And we played speech, and then we played time reverse speech, which is when basically speech played backwards, which sounds a bit like so it sounds horrible. You can't really detect phoneme onset or reliably anyway, or phoneme categories reliably. So the idea was, okay, let's use this phonemic model, this phonemic input that is just a bunch of zeros and ones to say a phoneme is here or not. And one hot encoding if you come from that domain of work, and relate that with the EEG. So these are multivariate models now that include both the acoustics and the phonemes. And what you're seeing on the left is how much more variance can we explain when we use this phonemic set of features. So when you look at the acoustic encoding, there are differences, and primarily due to attention. That's the idea, because you don't care about time reverse speech. But here, what we saw in how much variance can be explained by phonemes was that there was a significant increase over time reverse speech, and there was a significant encoding only for normal speech. And then we can look also at the weights that tell you which phonemes are represented when and where. There were lots of problems with the first study. With one study, you can't answer a question like this, but it was very exciting to see that we could measure this with EEG. So I got comfortable when, after a few years, people started to replicate this type of analysis. So Tom Frankart group, for example, and Lars as well has done similar analysis in his Science Advances paper. Laura Williams has been using similar methods. Then it's not that everyone is taking exactly the same thing that I did, but the concept of taking all of these features and studying the increase and studying the weights and so on. So I was very happy to see that different studies could see similar results. Also, I looked into different methods. So CCA, for example, that's one of the methods that I learned from Alain de Chevenier during my postdoc, and it's a better method than TRF for decoding, for example, and for mapping. It's better, but it's also more difficult to fit, and so there are some challenges there. There are also different tasks that we looked into, audiovisual processing and now sign language, which I'm very excited about. But today I'll talk about selective attention, which lots of us are excited about and have been excited about for 10 years now. And then looking at different cohorts, babies, children, and so on. All good so far. It was just an introduction. Yeah. So let me dive into it. So each of these studies might take half an hour to explain. So I'm just giving an overview of some of these that I think are exciting. So there is one on children and dyslexia. Then there is some work that I did on learning a language as a non-native speaker that is learning English, for example, and also as during development. And then there is ongoing work I would like to present, some of which is unpublished. So this is one I'm excited about. So Lars has mentioned it at the start in the introduction. So I'm very excited about this one. The project is a project led by Usha Goswami at the University of Cambridge. Big project, ERC, that now is over. The grant is over at least, but there is lots of other analysis that can be done. So this data set is shared, by the way. So I spent a good chunk of time to make it available in a way that can be analyzed with code and everything. So these were babies at 4, 7, and 11 months of age with data recorded longitudinally. So same baby, so 50 babies, and each of the 50 babies have been recorded 3 times. And they just listened to nursery rhymes for, I can't remember how long, something like 15 minutes of data for each session. So it's a decent number of recordings, challenging to collect. When we look at acoustic encoding, we're talking again about temporal response function, forward temporal response functions using acoustic features, so envelope and derivative in this case. We see that 4, 7, and 11 months of age, there is an encode. They encode sound, so it's not surprising because they can hear, and so their brain is going to respond to the envelope of whatever they hear. But when we look at the phonological encoding with the same method I described in one of the previous slides, that's where we would expect an effect. We would expect to see that there is an increase. So as they get older, they can process phonemes a little bit better, more consistently. But it is not that obvious. So the increase is obvious. It's not that obvious when they would start to reliably encode phonemes. So what we saw is that this encoding was reliable from 7 months of age. So you can see on the right this increase I was talking about. So there was also a control group of adults. So you can see more or less where this trajectory goes. And the empty dot means that it's not significant, and the dark dot means that it's significant. So there's large variability across subjects, and but you can see that 7 months of age there is significance that wasn't there before. So it's not obvious. Why is it not obvious? So there is a lot of work in the literature, lots of really interesting work, but most of that work is not with continuous speech. Most of that work is about discrimination. So there are tasks where you play different phoneme contrast, syllable contrast, and you see which contrast they can detect based on their turning of their head. So experiments like this are very important, but they're also limited in how many things you can study in one experiment, and also you're studying discrimination. Instead, when you talk about natural speech, it's not about whether you can discriminate one phoneme from another or one syllable from another. It's about, do you have a reliable and acoustically invariant encoding throughout an experiment where you listen to continuous speech, in this case, nursery rhymes. And it seems to be the case. So not shocking, but I'm excited about it. I think it's confirmatory, so it doesn't violate anything that we knew before, but it's exciting. So this metric, the idea is, can we take these metrics in infants and try to predict their language outcome 2 years after, for example? And so there is work, if you check out Usha Goswami's work and Adam Taheri, they also did this kind of analysis where they can try to predict language outcomes later on. What I did instead in some early work was something a bit different with the same metric, which was, it was the first time we tried to apply this to some particular cohort. And so this was on children and dyslexia. So we had 70 children, school age, so 8 to 12 years of age, and they just listened to an audio story. I think it was Winnie the Pooh, some Winnie the Pooh story. And there was a video that they could watch. It wasn't lip synced though. That would be a problem, because if it was lip synced, then it would be an audiovisual experiment. Well, the task was auditory. It was really, they were listening to the audio. But the video was just to grab their attention, was showing more or less what was going on, but there was no speech. It was not audiovisual speech, let's say. So what we could see was a substantial difference in the acoustic phonological encoding, so a mixture of the two metrics. And it was interesting because there was still quite a bit of a debate on whether these metrics were capturing really something related to phonemes. And what we could see was a correlation between this specific metric of phoneme encoding and phonological awareness and digit span. So that gave us a lot of confidence for the following studies. All good so far. The other exciting study that I wanted to mention is a study on second language, which I find extremely exciting. A couple of journals we sent it to didn't think the same. I think it's very exciting. So it's similar to the baby study, but in this case, it's not longitudinal. And also it's not on babies, it's on adults. So this was led by Nima Misgarani. And it's actually a funny collaboration because I started this project in France and I discovered that he was doing the same project, but he had more data already. So we joined forces and we did it together rather than competing. So these were native Mandarin speakers that were learning English at different proficiency levels, from A1 to all the way to C2. C2 is I'm C2, I think. Well, a native English speaker is a different category, right? Is maybe proficiency-wise they are C2, but they're like C2, but it's not the same thing, right? Because they learned it as they during development. So we had lots of participants. They listened to, these are adults, so they could listen to a lot of data. So 1 hour natural speech, same thing as previous experiments. So here comes the another way of plotting this data. So you remember that plot, the colorful plot of the phoneme model from before. It's hard to read it in that format because there are colors. So what is what, and you can't really see the distances. So what if instead we plot the distance between the TRFs for different phonemes on these maps? So these maps represent how far the TRF for a phoneme is from a TRF from another phoneme. And so we can plot this for native English speakers, that's the blue color, and for the native Mandarin speakers that are beginners in English. So participants only listen to English. Oh, someone is putting some notes. That's good. So what you can see is that there is a difference between the blue and the red. Okay, it's as simple as that. And I quantify the difference here on the bar plot on the right. Then we go to B level, and the difference is shrinking. And then we go to C level, and the difference becomes very, very small. So what's going on here? We're fitting these models independently for these 4 different groups, A, B, C, and L1. And I'm seeing that the distance, the closest group to L1 is the C level group. So it's obvious, right? It is obvious. Not 100% obvious, but it makes sense that the mapping gets closer. Doesn't necessarily need to be the same. So here you have a plot with all of the different groups and significant, and everyone is happy. But it gets interesting when you also compare this trajectory, what we could measure with infant learning. So I really get comfortable in saying, okay, this metric, I applied it in a number of studies, and it's robust. What these trajectories are in line with is the perceptual magnet effect, for example, from the literature. That's very interesting perspective. And it could be really nice to really collect more data from different languages, with different phonological distances between languages and so on. So I'll show you more results on this data set in a second in the context of lexical processing. But before I get there, I need to talk about these other metrics. So I talk about phonology so far, but really, as I was focusing on phoneme level processing, lots of other colleagues started to look at different levels of processing. I focused also on lexical processing, but then there are other people working on syntax. And this is a very old slide. I haven't updated it since 2021. So since then, there is a lot of more work on this. So one angle that I really like is predictive processing in the context of lexical processing. So I don't need to explain it to you. You already know what I'm talking about. But in brief, the idea is if you have some way to make a prediction on what's coming next at any level of processing, right? That prediction is going to impact our encoding, our response, and of that particular feature. So at the level of lexical processing, this is really close to what GPT and large language models do. So decoder-only transformers, right? They basically try to spit out the next word based on the context, right? So and so we can get those models and try to estimate how likely or unlikely is a word based on the context, and that turns out to be correlated with how to our brain activity from EEG, MEG, ECOG. So Nima Misgarani has a very interesting preprint, or maybe it's published now, on comparing different models, showing that newer generations of these large language models, they really are much better and much closer to how our brain works, which is a funny thing. It doesn't have to be necessarily like that. So this is the idea. If you have a word, the dentist told me to brush my tree, you have your local context, you have your prediction, and you have your prediction error. We can certainly, or most likely, we can measure prediction errors or things that are correlated to that. And that's why we use large language models together with other features. So in this study, the second language study, what I did was, and this was not the first study doing this, but it was a nice application. We took these surprises. I think it was, can't remember exactly which metric we used, which feature we used here, but it was a feature related to that. So, and we fit TRF, forward TRF models for these different groups. So each TRF is fit separately, independently. So for the L1 group, the result is consistent with what I had seen before with Michael Broderick and Edmund Lawler. So it's basically something that looks like an N400, also has a topography like an N400, and it's around 300 and something milliseconds. For A and B levels, you don't get much, while for C level, you get a significant response, still N400 looking, but it's a bit later. It's consistently later. So if you look at the topographies, L1 is more stereotypical, while for A, B, and C, there is something funkier going on. The topography is not as occipital anymore. There is more of a central and centrofrontal components, and so that was interesting. So we could talk about this for a while, but the point was this metric is sensitive to this learning, and the learning doesn't necessarily converge to the native speakers, right? Because if I am this guy here that is sea level, so my brain responses are not the same as the responses of Ed Lawler, right? So his brain works a bit differently than mine. Apparently, I'm 100 milliseconds slower, which I don't know if it matters or not. But yeah. So then we can take a more decoding approach, and we can try to decode proficiency, and taking lots of different features, it works. So on the y-axis, you have predicted proficiency, on the x-axis, actual proficiency. And then the other proof of concept is here. If you take your C level, so the L1 versus L2 is, we can decode it with almost 90% accuracy. Without doing any fancy machine learning here, this is all basic stuff. L1 versus C level, so me versus Ed Lawler, we can still say the difference. We can still tell the difference. So this is just to say, it's obvious, but my brain doesn't work like a native English speaker's brain, but we can try to pinpoint which features are different for people that come from different native languages, for example. That would be very cool to do. So I'm giving you a few snapshots. If you call me again in 3-4 years for another talk, then everything will make sense, because there is a reason for doing all of these different lines of work. It's just not as clear at the moment. But let me talk about selective attention for a second. You're all familiar with selective attention, decoding of attention, cocktail party. It's a very trendy line of work. Maybe the only new BCI I've seen in the last 20 years in terms of what metric we're actually getting, which is very different from previous BCIs, P300 speller, etc. Now, my take is more scientific than decoding, but I'll show you something about decoding. So this is an experiment we are running with one of my PhD students here, Sara Carta. Yes, my first PhD student is also Italian. But I promise none of the other students are Italian, so there is no bias here. It's very diverse. I have 4 continents and 3 continents, and yeah, all sorts of diversities. So, so immersive environment, 6 speakers, like speakers in the sense of physical loudspeakers, 2 possible targets, left and right. And then there is a speech bubble, a 16-talker speech bubble in the back. So it's pretty tough, but doable. Can't remember the exact SNR now, but it was doable. And the idea is that individuals they receive this cue. It's a simple greater or smaller, so it's an arrow that says right or left. So basically, if the trial is something like 2 minutes, can't remember exactly, something like 2 minutes, and they see a cue that says, okay, after 20, 30, or whatever number of seconds, it tells you, okay, now switch. So it's as simple as that. And there are comprehension questions to check that they're actually attending and so on. So the hypothesis is really basic, is that when you look at speech encoding, so not decoding, we're just talking about encoding. So what's encoded in the EEG? So the green speaker here, the speaker on the left, for example, the green speaker, will be encoded before the switch. And then after the switch, after a certain length of time, we'll just switch to the other. And in the same way, speaker 2 will be not encoded very well at the start, and then it will be encoded. And note that when we talk about encoding, there is a level of encoding of the unattended speech, because our brain encodes the acoustics of both to a certain extent. So the question is, how does this switch take place? Is it symmetrical? right? So is there a simultaneous disengagement and engagement? How does, which is what I draw here, how does, and also another question on the lexical level is, how do we use the lexical content to facilitate or to process speech during the switch? So we have context from one stream, right? And then we are switching, and then suddenly we are switching to another stream. And so we need to forget that we know that that's not the context anymore because we are switching. So we forget about it, and we might retrieve some other context. So we wanted to see if we can measure this and if things are as expected. So a couple of introductory notes. This is all inspired and follows the work from Ed Lawler, where I wasn't involved. This is before the study was done before my time. So O'Sullivan et al., highly cited paper. Something where I was involved instead is the Cocoa Hub project, which is a big project that was done through 5 different institutions. I was in Paris when we did this with Alain de Chevenier and DTU and others. So and Ericsson Research Center. So in this paper that has been published just now, just a few days ago. So it's in press actually, Journal of Neuroengineering, but there is a preprint. So this is, I think, this is the final paper of the whole project, which was a 5-year project, I think. And the idea was to build a device that is actually a brain-computer interface that steers the attention that detects who you want to attend to and amplifies the speech of that particular source. And so it's to build a device, it's complicated because you need source separation. And so you need the audio control, you need the EEG, attention decoder. So, and putting together into a closed loop is tricky. So it took a number of years. So this paper summarizes this more engineering effort, and it works. So in that paper, you can also see some attention switching and some application for hearing devices. But let's go back to the study I'm talking about here, which is Sarah's study. So the first thing we did was to run a classification, so a decoding of attention, which everyone runs now, just to understand on the sustained attention bits, what kind of decoding we can get, just to validate the data set, and numbers are compatible with what was seen before by Daniel Wong and others. If you want to see work where people are really trying to push this decoding to the best possible decoding, one interesting thing, again, where I'm not involved, is the ICASP auditory EEG decoding challenge. And there is lots of people that use some fancy methods to try to push these numbers up, making these models less interpretable and so on and so forth. So our study here is more of an encoding study. So the idea is, let's try to see what happens. Sorry about the colors. This is all very recent, so we haven't. So the purple is really orange. But the idea is, okay, this is the encoding of the 2 streams, and it's exactly as you would expect. We also looked at alpha, and interestingly, alpha seems to have a negative peak. So instead of being like full disengagement and instead of being like a step, it's something that goes down, it peaks, and then it goes back up. So we're trying to understand if this peak is more or less at the time of where the decoder would switch. But this, we think that this should reflect the switch anyway, and this is compatible with what someone else saw, Stephanie Harrow in EJN 2022. So nice validation. Now let's look at the encoding and the switch. So what we see now is, this is speaker 2. So this is the speaker that is initially ignored, and then it's attended. And the number, so the 0, 1, 2, 3 is a time from the switch cue. So you see here that it takes about a second and something before we can start seeing that there is this re-engagement. Now, interestingly, when you look at the disengagement, things are not symmetrical. So while at 1 we start engaging with speaker 2, speaker 1 is still encoded, and the disengagement really is much slower and ends later on. So we're trying to quantify this. This is preliminary. We're trying to we fit these broken line model fits, basically, to try to figure out when this transition starts. And it seems, from what we are seeing at the moment, and again, it's preliminary, that whatever decoding window we are using for our decoder, or whatever window we're using for our encoder, sorry, it's written decoding window, it's really an encoding window. But whatever window we're using for calculating our correlations, we can see this difference in when the transition starts. And so it's exciting, it's interesting, because I mean, the idea is that there might be a window of time where you're encoding both, maybe in different ways, and that might be related. And this is specifically happening for a model that includes acoustics and lexical surprise. And lexical surprise seems to be important. So the idea could be that you might be primed, and there is context on your speaker that you were attending to, and so you might be able to keep the encoding for a bit longer, as long as that context is relevant. So it's all preliminary. The other thing is talking about lexical expectations. When you switch, let's say that you switch over here, or let's say, sorry, can you see my mouse? So let's say that you're trying to predict. So we are here. We're trying to figure out what is the lexical surprise or lexical expectation in general for the word over here. So what is the context for this word? Now, in an oracle model that is a virtual amazing person that can attend to two speakers at the same time, right? Then the context would be the entire blue rectangle here, because they would be able to pay attention to the entirety of that material. Something more realistic is, okay, this person is switching here, so the person knows that this context is irrelevant. So they're going to get rid of that context. And then the only thing that is available is what they just heard and what was heard maybe before at the previous switch, if that's relevant. So we just fit two models based on these assumptions on these different contexts. So numbers are tiny. So we had to develop a whole new improvement of the metrics we generally use, and we have a preprint on that. But basically what we see is that this model, this speaker-specific model, is more appropriate, is more correlated with the EEG. So is it obvious? I think it is. I think what would be interesting to understand is, with a more tailored experiment, whether there is evidence that we're getting the gist of the unattended stream, but whether we use that for predictions or not, that's less clear. So we could have an experiment where we can get the gist, or we don't get the gist, depending on the information on masking, for example, acoustic masking and so on. So anyway, but methodologically speaking, it's interesting in that we can compare different models with different lexical context and see that there is a difference. It's small, but it's significant. And so the metric we are using is described in this paper down here. So it will be in the recording. How much time do I have?
Maybe 10 more minutes?
10 more minutes. Okay, thank you. So I'll do this briefly. Sorry for Giorgio. So Giorgio is great. He ran this experiment between BCBL and Trinity College. So he had two groups of speakers, native speakers, non-native speakers. Anyway, each of these groups, they listened to speech that was foreign directed speech, native directed speech, and then a control speech that was a slow native directed speech. So it's an artificially manipulated native speech, so that it is a bit slower. It doesn't sound artificial; it sounds actually good. But it doesn't have those inflections that you would have in foreign directed speech. The lexical content is the same, just the acoustics change here. So acoustically speaking, there are differences. So if we get, and I'm sorry I'm going very fast, but the idea here is that you get non-native speakers in this case. So these are Basque native speakers, I think, or Spanish native speakers, or a combination of the two, I can't remember. but there are non-native English speakers that listen to these three conditions, and foreign directed speech is the most strongly encoded, and the other two are a bit weaker. But it's hard to know what's going on until we look at more specific features. So with the phonological encoding, again, so I'm obsessed with phonemes. Phonological encoding, what we see is that the speech register matters in terms of distance. So we are looking at the same distance I showed before for the second language study. So the foreign directed speech, listening to foreign directed speech, gives you an encoding of phonemes that is closer to the encoding of native speakers. So the idea is that it allows you to encode the phonemes better. While if you listen to native directed speech, the encoding is not as good, and it's the same as slow native directed speech. So basically, slowing down your speech is not enough when you talk to non-native speakers, at least in terms of phonological encoding. Georgia also has results on lexical processing and so on the preprint. So that's an interesting angle. Let me conclude with music. So I would like to talk for another hour about music, but the concept is the same. Talking about predictions, you have a context and you have a next note, so you can get use music transformers or Markov chains to say how surprising is the next note. So you can study the same type of processes. So I just skip through. So it's the same type of model, and the music. Let me know if you hear the sound. Could you hear it? Yeah? No? Okay. So it's just a melody with one note at a time, and it's piano, and it's Bach in mostly, because I like Bach. And the idea is, okay, we have melodies, we have acoustic envelope, derivative, acoustic features, and then we have surprise features, surprise of pitch, surprise of timing, entropy of pitch, entropy of timing, and we have EG and ECOG. A little bit of ECOG, that's through Nima Mesgrani and his collaborators in Columbia. So the idea was, okay, let's see if we can explain more EG variants with these surprises, and we can. The increase in the amount of variants we can explain in addition to acoustics is really small. But when you look at the single subject, it's actually consistent across subjects. So it didn't scare me too much that the numbers are small. We can do a number of controls. In this case, I messed up the model, making the model predictions less good. And then the model, this increase disappears. And what we found was, yes, that EEG signals reflect melodic surprise. But then we also saw that this effect was in planum temporal, but not in primary cortical areas like Heschel's gyrus, and that's with ECOG. Now the EEG results, and I'm really excited when someone replicates your results, I think is one of the best feelings. The climax is gone, because maybe you published this 3-4 years before, but it's great. So there are studies. I think Lars, you were involved in one of these actually, that reanalyze some of this data. I think in the second one. Well, the first one is from. Oh, right, is that you? Okay. And then there was Ross Maddox's lab that did the whole new data collection with the chimeric sound. So that's very interesting study as well. So it's nice to see that certain effects emerge not from me. Otherwise, you would get nervous if it was just me that could find these things. So this is ECOG. I'll skip through. It's the same thing I said before. So there are last thing. So there are a couple of things I would love to talk about, but just one. So why is this relevant to speech? One way it's relevant to speech is through this study. Georgia, and this is on bioRxiv. Georgia, everything is on bioRxiv. all of the studies I'm talking about. Hopefully they'll be published soon. So Georgia played speech, sung speech, and melody to 20 subjects, I think. So the sung speech and the speech, they were recorded by someone else, some data sets we found. And the melody was a transformation, with an algorithm, a sung to hum algorithm that transformed the sung speech into a hummed melody. So all the linguistic content is gone. but the acoustics is the same, the acoustic in terms of envelope and the timing, etc. Just to narrow this down, let's just look at the song and melody conditions for now. So the acoustic encoding, there is really no big difference between the two. That's okay. I didn't really have a hypothesis there. What's exciting is that when we talk about melodic surprise, we can measure it in both. We can measure melodic surprise in melody, and we can measure melodic surprise in song. But in song, there is more than melodic surprise. There is also phonological, phoneme level surprise, calculated with, can't remember if it was a GPT model again. Heilbron, Misha Heilbron proposed, I think it comes from him or maybe before him, but I think we use his method, but we need to ask Georgia the details. But the idea was that, okay, you have the song condition, you have melody, you have phonological information, then there is more, of course. But we like to compare these two levels that are at similar timescales. Not exactly corresponding, because then oftentimes the note corresponds to the syllable rather than the phoneme. But you can see that there is actually a significant effect of lateralization here. So the song appears more on the right and the phoneme appears more on the left. Now, this is not a surprise to see lateralization, with speech and music and so on. So why is this exciting for me? Because I had never seen lateralization like this with EEG, continuous sounds. I just hadn't seen it. So I didn't think it was even sensitive to it. But it tells me something, that this lateralization emerges when the two things are happening at the same time. The two features are present at the same time. As if where you look at the previous plot on melodic surprise, there is no hint of lateralization. Again, it's EEG, so let's not be too excited about the sources. But getting some lateralization when the task is more difficult, it tells us something, I think, about the competition between these two processes in a way, or at least parts of it. And then she could find all sorts of effects. One effect was effect of training, musical training. So individuals that are more musically trained, they show stronger preference for melodic surprise as opposed to phoneme surprise. As opposed to an encoding effect, I'm better musically trained, so I encode better melodic surprises. Maybe it's just an effect of attention. They might care more about the music. So that's still to be clarified. Okay, so before concluding, let me just do a little bit of advertisement of my efforts and efforts of others. So I've been involved in an open science initiative. It's called CNSP. Stands for Cognition and Natural Sensory Processing. So we started as a workshop, and we have lots of interesting video tutorials, especially online. So if you look at the cnspworkshop.net, you can look at all the videos of the sessions of the CNSP Workshop 2023. Now, there is a component of new science, and that we like to invite speakers that do different things, etc. But there is also a component of tutorials where we take some of the resources that some of the models I use in my work and others of the team use in their own work, and try to share it in a way that can be used promptly. This includes datasets. So there are quite a few datasets now in the list, and all of this is focused on datasets that have an X and a Y, that have stimulus features and have an EEG signal, an MEG signal, or whatever continuous signal that you might think of. So it's still a small community, still a small set of data, but I think it can be really useful. And it saved me a lot of time. For example, it helped me training my own PhD students or master students, because these are resources that I say, go look at these things, these methods, and then run them, and then come to me when you know how to run them, because everything is in there already. And there is more in there. So there's going to be a workshop in 2025. It's to be announced. So this is just a pre-announcement. We are thinking of doing an online workshop in 2025 around August, And then we are trying to organize an in-person hackathon as a satellite of another event that I really like. So hopefully that will go through, that will work out. So I'll conclude. So I presented a number of snapshots of the kind of work I do, and we are moving towards even more naturalistic scenarios. So the idea is, I think this work demonstrates that we can study speech and music with ecological varied stimuli. I don't think there is any doubt anymore. It's not only my work, it's the work from lots of other colleagues that did this independently as well. We could objectively measure these learning trajectories for speech processing, sensitivity to dyslexia, sensitivity to other things that we're working on autism now as well, and other things. So, and then this idea of prediction error surprises, they can be measured with speech, they can be measured with melodies, they can be measured together. So let's try to understand the commonalities between these mechanisms, which goes beyond saying, oh, it comes from the same cortical area, right? It might be not as important that it happens in the same place, but the question is, does it work in the same way? And yeah, and finally, yeah, it's that's what I said. So it's encoded simultaneously. That's it. Thanks a million.
Thank you, Giovanni. This was a blast. It's fresh and it's like the right experiments to do first, and it's like clear-cut results. I don't have any questions, but I'm assuming that other people in our audience have questions. Maybe we start online in good tradition. Just raise a hand or type something in the chat, and then Carl was happy to unmute you. Nothing yet. Maybe in the room? Everyone's just blown away. I always had a question I can ask you today. The L1, L2 distance with the for the single phonemes where you show the first and second eigenvariate in the coordinate system. How exactly do you do this? Like, what do you do? You take the TRFs and PCA them and just take the first and second eigenvariate and do that for each feature and then you plot them, or what's the...
Yeah, it's a good point. So I've done it in a couple of studies now. That was the second time I tried it. So you basically take your TRFs, your TRF weights for all electrodes. So you just flatten that, just take all of that.
Yeah.
And you project it with the PCA, so a multidimensional scaling. Scaled multidimensional scaling in that case. And then this was particular to this study and to the baby studies as well. The problem is that all of these spaces where you're going, they're all different because they're different projections. So what I did is that I calculated them separately, and then I did a Procrustes analysis. Procrustes analysis is a linear, it's just a rotation, but it's a simple rotation. The only thing you can do is to rotate and scale. And so you're trying to match one on top of the other. So that's why they look one on top of the other, right? Yeah. And then you can check the distance. There are other distances you can get as well within each space. But I like doing the Procrustes because then you can visualize it and it makes sense.
Yeah. That would work for MEG as well, right?
For any what, sorry?
That would work for MEG just the same way, right?
Yeah. Yeah, okay. And you know, one thing I remember Jordi Martorell, he which you were in a study with him as well. Yeah,
he was here until half a year ago, yeah.
Right. He was here for 3 months. He did a project partly with me, and he so we were wondering, you know, when you talk about MEG and maybe you have, you know, different dimensions, how do you combine? So you either work in source space, but what if you don't want to work in source space? You might, so in this case, for this kind of analysis, you can combine everything and project everything, and the model will figure out whatever is most relevant for you. Same thing for a decoding analysis. You don't need to go necessarily in source space. You can just take everything at the same time.
you just would scale up your data anyways, right? When you have like you don't add anything when you go to source space. But then I'll be in touch actually because I have a data set that might be worth for applying this.
Yeah, sounds great.
No, thank you.
Okay. There's someone that has a question.
Mm-hmm. We cannot hear you. I'm sorry.
You type, yeah. You're not muted, but we can't. Yeah, it's your microphone maybe. That must be a very scary question now. So thanks for the great talk. In the card that I'll study the timeline for engaging, and there is a strange feedback. Is it from you? Sorry, I muted you because for some reason there was some strange feedback. In the card that I'll study, the timeline for engaging, disengaging is over a second. What type of info was encoded? Lexical. Yeah, that model was a model including envelope. Was it the derivative? Can't remember. Certainly envelope, word onset, and word and lexical surprise. Now, it caught me exactly at the time where we are looking at that. So as you are asking me this question, I have an email from Sarah with in an ANOVA table on exactly that analysis. So what we're trying to do is to figure out what features are really driving this this delay, which seems to be might be more related to the lexical component. What we're also trying to understand is, everything is through forward models here. Exactly because with forward models, we can combine these different features. But we were originally trying to do this with backward models. So where we try to reconstruct the envelope or reconstruct the word onset or the word surprisal. The problem is that then, these are all separate models, and you compare a continuous feature like the envelope with a discrete something like the word surprise. Also, I would like to use the decoding models as well somehow because they are better in a way in terms of the mapping itself. Like classification accuracy is better for the decoding model. But I couldn't figure out a way to do it. CCA might be a way, but then it's harder to interpret. So at the moment we are kind of stuck with the forward models. But yeah, lexical. That's my answer. Thank you.
Who's next? Yeah. Then okay, Camilla, please.
Hi, thanks for the talk. I was wondering when you compare groups in your TRF models, for example, in the language learning experiment, and you compare the TRF weights between groups, how do you do with the regularization parameters? Because I guess you use different parameters for different groups, and then comparing the weights, the weight would be affected by the parameter, I guess. Can you comment? Thanks.
Yeah, it's a great point. So that's not an easy question. So now, ideally, you would not do anything to those parameters. So if you had infinite data, right, then you don't have the issue of overfitting really. If you have infinite data, and so your parameters, you could just run the TRF normally, and it wouldn't be an issue. While when you have very little noisy data, that might be a big issue because, of course, as you're saying, Camilla, the higher lambda means a higher smoothing, and then you're comparing TRFs that are very different, because one is smooth and the other is not. So there are a few tricks to make the comparison fair. So for prediction correlation, it's not a problem, but for the weights, it can be a problem. So for the second language model, second language study, it's not a problem because there was a lot of data. So basically one way is you just do it, let the model figure out the lambdas, and then you check if there is a big difference. And there wasn't in that case. With the baby study, it was a big problem. And let me try to remember how I did it. The idea is there to use generic models. So instead of using, try to remember, I can't remember the exact details. I will need to go back to the paper. It's just a year and I forgot. But the idea is that instead of having many different models, let me think. That's embarrassing. I can't remember.
Maybe use the same for all of the groups.
No, but you see, the problem is, what is that same lambda? Yeah. What is that same lambda? You just say, I've had colleagues that ask me, oh, I just use lambda 1. I'm like, no, you can't just pick a random lambda, right? Because then what if your result changes for a different lambda? So you need to have a criterion to pick it. Now, if I remember correctly, I did what you said. So I picked a lambda, but I picked it based on generic models. I picked it based on generic models. Generic models is when you fit a model combined on, you combine a bunch of subjects and you try to predict another subject, for example. So it's a model that is not trained on that particular subject, for example. But there was a smart solution. I need to get back to you. I need to look at the paper exactly to know exactly what I did.
I can look at the paper, thanks.
And I think whatever I did, I actually have the exact code I use for doing that. So the link is on the CNSP workshop website, but it's also on the paper, linked on the paper. So you go there and you can check exactly what I did with the regularization parameter. I don't want to lie now and tell you one rather than the other. There are a few ways you can do it, but I'll need to get back to you. Could you drop me your email or maybe I can, if you drop me your email on the chat, maybe I can reply to you later. It's in the paper anyway. I can't remember. Sorry.
Maybe you put me CC on that email, because I've seen papers where people actually use the mean value across subjects. So they do a cross validation within subject, test like 100 parameters, and then they just take the average parameter. And I've seen that. I just don't know whether that's the way to really do it. Yeah, whether it harms certain data sets, because you always have variance in the lambdas that you're estimating from the data, right?
Yeah, I'm trying to open the paper now to see if I remember what the trick was. I'm sorry, I have a moment where I can't remember. But I don't think it is appropriate to just pick the average. Like, it's better to pick the average lambda than picking a random lambda, like 1. And I've seen that published, So the thing is that I don't think it's a disaster, but at the same time, I don't think it's correct either.
I wonder how it affects if you want to run individual analysis, like for each subject, and then you're using a single lambda. You're not being fair to all of the subjects in the same way, I guess. So the same lambda would fit some subjects better than others. And then if you want to compare like individual scores, I
had a very good, oh yeah, wait a second. Sorry, I'm reading the paper as we speak to try to remember. There was a concept there. Yeah. So what is the problem? If you have little noisy data, you have lots of variability. Some subjects are literally, it's not the subject that is rubbish, but the data is rubbish. It's not enough. And so the model tends to over-regularize. So ideally, you would have either more data or some trick to get better, more reliable prediction correlations. So what I did in that particular paper was to define a ground truth. So you take all of your EEG data from different subjects. Again, big assumption, assuming that all they respond in the same way, which is the same assumption of an ERP, of a grand average ERP. So I'm not creating an assumption there. Still big assumption, no doubt. So you take all of your EEG and you create an average subject. It's not the best way to do it. The best way to do it would be to run MCCA, which is another method from Alain de Chevenier or something like that. Because MCCA doesn't have the assumption that everyone has the same topography. While if you average, you assume that everyone has the same topography. You take every electrode, you average, you assume everyone has the same topography. That's wrong, but it was overcomplicated. It worked using MCCA, but the reviewers found it too difficult to explain. And they said if the average work, use the average. So we just average all the subjects. Then we fit single subject TRF models, right? Same as before, same as the usual. But instead of getting the correlation between your predicted EEG and your real EEG, you do the correlation between your predicted EEG and your ground truth with leave one out cross validation, so excluding the data, etc. So what is the impact of this? Is that your prediction correlations now are more stable, are more reliable, and the lambda won't tend to over-regularize. You don't need to have a massive lambda because you're. So what happens is that the TRF might look good. That's one observation we did a few years ago. The TRF weights might look decent, but the prediction might be terrible just because it's so noisy. You can actually test it. You take a TRF out of a terrible subject that has poor prediction correlations. That TRF might work on some other subject because the weights might be good. It's just they can't assess it properly. So we got the ground truth, but then we still did the fine-tuning, the regularization search.
Can I follow up on that for a second? So if you have bad prediction accuracy, do you just not interpret the TRF weights?
So that's a good point. So if you have enough data, like if you have an hour of data and your prediction accuracy is poor, then your feature is not good. Your model is not good. You don't interpret the weights.
Even if it looks as expected.
I mean, if you have as much data as you would expect to work, then if a subject works and the other doesn't work, then it's probably poor data, right? Which can happen, you know, the cortical folding, etc. Some responses don't get up for a subject, but in that case, we know that those responses were good. It's just that we have very little data, very noisy data per subject, so the correlations were just too unstable. And so the ground truth trick, which is similar to what I had published a paper on that, on something similar in 2017, that looks at these generic models, these average models. This is a bit different, but still the idea is let's try to get single subject models, but let's assess them on something that is more reliable, more consistent. So it's a trick, and yeah, that's how I did it.
Thank you.
Thank you for the question. I had completely forgotten that part, but I remember it was at the time I was excited about the idea because I thought, oh, that's a good idea. But I had forgotten it. Stephen.
We have two more. Let's see. I think the first one was a question in the chat by Ray. There's two questions, and then it's Stephen. Yes.
Okay, so the question is, thanks for the nice presentation. I have two basic questions with the study on music. Could you please give a brief explanation on how do measure the level of surprise parameter? So the surprise can be measured in a couple of ways. The way I did it at the start was by following the work of Marcus Pierce, who defined this model called the idiom model. It's called a variable order Markov chain. So it's a Markov chain, it's a Markov model that basically adapts to different lengths of context. So Markov chains are basically, they tell you the probability of a transition, and so you can reverse that and tells you the surprise, or the way he calls it, the information content. You can also do it with transformers, so more closer to a GPT, LLM. In this case, it's a music transformer. So we tried with a couple of transformers, and whatever transformer we tried, it works. What is the difference? Misha Heilbron has also a nice paper where he was working on something similar. what is the difference between musicians and non-musicians on that measurement? On the e-life, yeah, I mean, again, it's 10 subjects, so I wouldn't be too excited about what we can see in 10 subjects, but we did see some differences. Generally, you see that, you know, the encoding for musicians is a bit higher, maybe, but in the kind of effects I've seen, that kind of data is relatively small. So I think Lars and I'm sorry, what's your name? I can't remember. On the left, Lorenzo, no?
Yeah.
Yeah. So you maybe have seen more effects of musicianship. I wouldn't like to comment too much on that though, because again, it's just 10 subjects. Yeah.
So like my former PhD student Vincent Chung, he had data where he tried to build such models on different levels, so acoustics versus abstract levels like chord symbols and things like that. And he found that this non-musician difference is stronger for the more abstract levels, right? So if you're trained and you know about chord sequences and tonic and dominant and so relationships, abstract relationships, syntax, then you get stronger expertise effects. For the more low-level acoustic/melodic ones, they are not as strong. I'm not a big expert on music, but I think that's kind of the general idea. Yeah.
Yeah, and it makes sense, right? It's not that shocking that someone that has more expertise, you know, the proper musical training, then they have better encoding of certain more, you know, higher features. So I'm not too excited about that. But it is true that there are some complications like attention there. Like in Georgia's study that I showed before, and we showed the musicians they attend, they seem to encode better melodic surprise as opposed to phonological level, phoneme level surprise. But that could just be that they care more about the music than the it's true that like this was an experiment where the acoustic was the same because they listened to the same thing, and there are two features within the same acoustic, so it's different than attention in the sense of, oh, I'm steering my attention to this speaker or the speaker, like the cocktail party. But in general, I think the literature agrees that there are some effects. I think we need a bit more data though to be like, okay, what is it of musical training that really leads to this effect, you know? Yeah.
Yeah, then it's Steven now.
Hello, can you hear me?
Yes.
Hi. Thank you for the talk and for your work in general. I have a question about when you do an MTRF analysis, when you want to predict, for example, the speech envelope from EEG data, is it possible theoretically to have some negative prediction or negative R values? I'm asking to add a bit of context. I'm doing a dichotic listening task, and I did it on different groups of bilinguals. And when I use a backward modeling, I usually find some very strong and very positive R values. But I was curious to look at a specific frequency band, alpha, and in the most difficult condition, and in a group of bilinguals that I expect to struggle the most, I sometimes seem to find some consistent negative R values, which seem to differ from zero. They're not very strong. Again, it's alpha, so with speech envelope, you don't expect to find very strong encoding. But I was just wondering, theoretically from that model, if it's possible to find some negative, and what does it mean?
So can I be direct? So my direct answer is no, but let me explain that. So it's a very machine learning angle to it. Now it's possible to have negative inverse relationships. So a negative weight that says a positive change in your input leads to a negative change in the output. But when you talk about prediction correlations, now you can have negative correlations, absolutely. Whether they do mean something, that's a different story. So, for example, take your O'Sullivan 2014 cerebral cortex paper, 14 or 15, I never remember. I think it's 14. There is a nice plot with a cloud of, of data points. And you see that, sure, when you talk about decoding of the envelope, maybe the centroid is positive, but then lots of these numbers are negative. That's noise. in the past, I got questions like, "Oh, but so can I put them to 0?" And like, no, don't put them to 0. It's noise. Let's keep it for what it is. Why shouldn't you get an average that is significantly negative? Because if you do a cross validation right, if you have 2 folds, for example, let's say you have 2 folds, then it can be negative, because in one fold you might get a TRF that is flipped compared to the other fold, and so maybe the prediction is consistently negative. But if you have 10 folds, if you train on 9 and then you test on the 10th, the prediction correlation tells you whether these are consistent, right? And because you're swapping around all of these combinations, you shouldn't really get something that is consistently negative, because it would just mean that your model is not working. Generally, the cloud, if it's not working, goes to 0, something negative. But now this is my take. I might be wrong. If someone in the call has another idea, but my take is that negative prediction correlations, when you have like a 10-fold cross validation, it doesn't mean anything.
Okay. Sure. Thank you.
Sorry, and you find something when you have something like this. Maybe there is something else, that some result behind that. Maybe there is a bug, and then something else comes up. But I wouldn't interpret a consistently negative correlation, also because I've never found one.
Okay. Yeah.
But if you struggle with that, I'm happy to chat more offline.
Sure. Yeah. Okay, that would be nice. Thank you.
Sure.
Sorry, I think it's about time to end this beautiful and very Italian meeting. We will now go, of course, for a red wine and Taralucci. Yes, my favorite. And, I wish you all a beautiful good night, and thank you again, Giovanni, for making it to the language circle. Everyone, don't just leave. The Italian saga continues tomorrow. We have another special feature of the language circle, so I'm very much hoping to see you all tomorrow again. Take care.
11 a.m. 11 a.m.
11 a.m. Goodbye. Thank you. See you.
Thank you, everyone.
Ciao.